in order to deal with safety criteria, which we have said in the previous video, and we actually call this safety criteria as the yield criterion, talking about the yielding portion. And that when we talk about yielding portion, we are going to first talk about what is the phenomenon of yielding, or what causes yielding and things like that. Then we can set up the criteria to do with things. So how do we start? See that the yield stress, alright, somewhat comes from here. Alright, we can call this also the yield strength of the material. Alright, and we know that once you exceed this yield strength, alright, you're going to start to have a plastic behavior, alright, which is shown over here. Alright, plastic behavior. And this plastic behavior means that you're going to permanently deform your materials. Alright, permanently deform your materials. So any stresses that acts more than this yield strength, alright, we're going to permanently deform your material. To start, if you have a certain cube over here, this is a solid cube. Alright, and I take a small dx cube. Alright, a small d cube over here. Alright, so if you were to combine all these cubes, you'll form this big cube. I'm just taking this little piece of cube over here. Alright, and zoom it out. So I'll just draw some other cubes besides it. Alright, some other cubes over here. So in other words, I'll have something like this. Alright, so these are all the little cubes over here. Okay, we have a stress of at a 3D space, we write as a cross, right? So this stress in the 3D space is maybe this particular purple line plus another particular vector that comes into the z-axis. So it's somewhat this one plus this one plus this one will somewhat give you some stress state at the particular 3D space. So this stress state is somewhat your forces that is acting on the surface of your material itself. So when you apply these certain forces over at this particular point, you're gonna initiate a certain stresses along these planes. Alright, maybe I should also draw another cube at the bottom of your stuff over here. So like this. Okay, so far so good. And therefore, if you were to visualize that this particular stress state is coming out towards your picture, towards you right now, right? They're coming towards you right now. I don't know how to draw because it's 2D in the TV, in your laptop now. So if you were to pull in this direction, alright, the rest of the plane is gonna follow. Alright, and therefore the outcome will be something like this. If you were to pull it in this direction, you're gonna somewhat bring all the cubes to a different direction, right? This cube's gonna go all the way in a different shape. Right? Just imagine that when you pull this thing, how do these 3 cubes behave? How do this 1, 2, and 3 cube behave? It's gonna somewhat collapse and follow this direction of the force, right? So they actually somewhat become more and more nearer to trying to be pulled in a certain directions. So this pulling of the force gonna initiate another surfaces that will cause another cube to follow on, maybe another shapes like this. So other cubes will actually be pulled. So in other words, at the end of the day, you'll see something like this of your general big cube, alright, which is over here. You're gonna somewhat elongate at this piece. If you were to go into side view right now, you'll somewhat see something like this. Right, so this is something that you pull, and then the rest of your plane over here will gonna be pulled also. So these are the little red cubes and the red cubes over here, blue cubes and whatever. So they will follow all along this side. If you were to just see what is, somewhat the point U. Alright, because when you place a certain stress at this particular point and then you pull it, so this yielding actually causes the particular point U over here. Alright. And however, how do you model this thing? Since you already visualize how the yielding would be created, alright. So in order to do this, we're gonna base on this surface, because the first thing first, when you apply a certain force over here, the 3 cubes over here, we're gonna initiate a certain force to other cubes that is related to this particular primary cube, right? So therefore, the rest of the cube will also follow up, which later on it will become somewhat a distortion of the shape itself already, right? You have to talk about it in, pulling it all the way like this. And therefore, to model this particular stress over here, alright, with regards to these three planes, let's redraw this axis, alright? This is some of basis vector, alright, if you were to take a look in terms of this particular region over here, alright? So I'll usually pluck it out and becomes like this, alright? And you can model your particular stress point over here, which is coming out by its so-called stress 1, stress 2, and stress 3. Okay? Or in other words, stress 1 plus stress 2 plus stress 3. Alright, going to the point. If you were to just, if the point, for example, is over maybe here, okay? So stress 1, and then go to stress 2, and then stress 3. Something like that if you were to take a look. So it's going into 3D, somewhat 3D lah. Okay? So when you add up all the stresses, it should be straight line actually. Wait, this should be better. So your stress 1 plus your stress 2 plus your stress 3 will give you your particular stress point that you would want to pull, right? So when you pull this particular stress point, you actually causes all the planes to actually moved, because you're dealing with stress 1, and equivalently the stress 2 is actually over this side, and stress 3 is this side. Alright, this is stress 3, this is stress 2, but I'll just simply move this vector towards this side to show you that it's more clearly defined for this particular point. So if you were to add out sigma 1, sigma 2, and sigma 3, what you have is particular point over here. Alright, just to show you visually how it goes. Alright, now if you were to apply a certain force, alright, this is the initial force onto the initial undeformed cube over here. So if I were to apply a certain force over here, up to a certain U strength, alright, up to a certain U strength, if you're larger than the U strength, alright, if your stress is larger than U strength, you're going to start to deform your stuff, correct? So in order to do that, to show you graphically when does U reach this point, alright, if you were to reach this particular U strength, then it will start to deform. We're trying to see something of that criteria, right? Because we're talking about the U criteria. So what is the criteria that ensure that a certain stress that you input, alright, will reaches this sigma U strength such that more than the U strength itself will deform your stuff. Okay? So therefore, this surface over here is the surface. If you were to look in terms of the 3D now, alright, this is somewhat like this. So your surfaces, there is somewhat like a circle to you in a 3D form, alright, is somewhat your boundary of your sigma y, your U strength, alright. So if let's say we know that this is your sigma 1, your stress, the stress that you have put in, right? So if your stress over here, all the stresses that is within this particular black box over here, this is considered safe, right? Because you actually didn't exceed the U strength, alright. However, if you have something that is larger, a stress 1, maybe this one is stress 2, maybe your stress 3 is over here. So you somewhat have another curvature that is outside. So you're gonna distort your shape in a different way, right? Somewhat like this, or maybe I use a clearer color, somewhat like this. You're gonna distort this shape, and therefore you're already out of the criteria that you required, and therefore you are permanently deforming in this direction, right? Because your sigma 1 is actually larger than the rest of the sigma 2 and sigma 3. So you'll cause certain deformations in this direction. Okay? Therefore, this black curve over here, as we have drawn, is actually your bounded area, somewhat of your bounded. So anything that comes out of it is considered unsafe. So this so this bounded is called your criteria, that anything that comes out of this bounded area will be unsafe. or will not unsafe, but then you'll start to yield. Alright, you'll start to yield. So this is your yield criteria. You may wonder, why is it this shape? Why can't it be a square? Why can it be a triangle? Why must it be this form? And this form actually reflects this part over here, your yielding part. Alright, this part. Alright, normal stress strain curve may not be like this. It may be like this. It may be like this. I don't know. But so therefore we just take the very common arbitrary curve that indicates that it is a non-linear. So this is a very clear curve showing that it is a non-linear curve to a certain extent. Alright. Or if it's just to show you, this is the one that I'm talking about. So this particular point is your hardening part, if you were to just say in that manner, or it includes your yield strength. Alright, so this particular curve is something that deals with what we are doing. Alright. And if you were to if you were to take a look in this plane over here, sigma 2 and sigma 1, if I were to draw it out, it's over here. And in fact there is some significant meaning behind there is an embedded system that is talking about the strain. So if your stress 2 increases, alright, your strain is going to increase. Right? So I think you get what I mean, because when you increase your stress, maybe this point, you're going to extend you're going to elongate your material. Right? You're going to elongate your material. And this strain is somewhat reflected over here. So if the further you put in your more stresses, you're going to further elongate your stuff. So therefore, this somewhat relates to your this curve over here. And this particular point reflects every point of this zone over here. Alright, all this point of this zone over here. So if you were to plot this point over here for all zones, it will be something like this. Alright, if it's a 3D, then it's something like this. Then you have to further plot maybe this particular point. You're gonna have maybe a green color one. You're gonna have a larger so-called strain. If you're gonna further plot over here, maybe this point over here, you're gonna have more strain. Or in that, so therefore this graph doesn't generally only show the stress, but can also reflect your strain, also reflect your how the thing move. Alright, and once you reaches this particular red color one, which is your criteria, and if you were to exceed, it's going bigger and bigger, this means that you're going to yield, and therefore it starts to yield. The yielding initiate, okay, when the yielding starts. So therefore this is somewhat a gradient, as you can see. You're drawing a gradient right now, okay, and therefore this explains the picture. In your chapter 29 textbook, alright, the first few pages talking about the Westergaard stress space. So this stress space is the spaces that we have been drawn over here. Alright, this is the space that he indicates. Anything that larger than this space, alright, will be yielding, that yielding will occur. Okay, that is the criteria that he wants to say, right? However, the constraint is that this shape over here might not be exactly a good shape to represent different material. Alright, this shape may represent maybe for other materials, maybe 30 materials, or maybe 50 materials. But we're talking about other materials that deals with shear stress or not hydro, but a different stress strain curve like this, instead of the one that we have drawn just now like this. Alright, it may be somewhat like this, and then like that, also don't know. Right, so these are the little things that actually cause us to actually deviate, that the criterion, this criteria is just not adequate enough. Although you can actually model all the points and model your criteria, but for other stress strain curve, you require a certain other shapes. Your criteria may be something like an ellipse, alright, and then this may be another form like this, I don't know. So this criteria may be slightly different from the one that you have seen just now, right, from the black one, which is, or in other words, I redraw. It may be different from this, the one that we have drawn just now. It may be something like this, alright, the base may be ellipse. Alright, maybe I should erase this one, because I just want to show that if you draw, it may not draw in 3D. I mean, like the negative and the positive side, you may see some form. Alright, so this thing may be something of a curve, a steeper curve. Alright, that may deal with an ellipse. Alright, so this curve is totally different from this curve, and the criteria will be slightly different. And then you also talk about, and therefore this is called somewhat the von Mises. Alright, the von Mises criterion. And then this one is criteria that is somewhat like a square or something like that. This one is called the Tresca criterion. Alright, so the different shapes will give you a different criteria that we want to see. Alright, therefore in the next video we'll briefly talk about the von Mises, because it's really tough to visualize all the shapes and the meaning behind the books that is telling us. I really don't know. But let's just talk about the von Mises first in the next video, and then in the next video we'll talk about Tresca, and then we'll link all of them together and see what is the result. And I shall see you there.